Good evening, everyone. Welcome to the Mound Science and Energy Museum Association webinar presentation on November the 18th, 2020. My name is Bob Bowman, and I'll be your host. And tonight we have the pleasure of having a science presentation by Dr. Bob Ellefson. And his topics it's going to be the use of isotopes in radiological tests and treatment. And rather than give you his long pedigree, we're going to start with his presentation.
Good evening and welcome to this talk this evening on the use of isotopes in radiological tests and treatments. Medical specialists need imaging tools to see a problem with a patient so that they can actually treat the problem. So from discussion with the patient, you can figure out their symptoms and choose appropriate diagnostic tests to be run to reveal what the problem is, like looking for broken bones or tumors or other non-normal features, problems with blood or fluid flow obstruction within the body, identify areas where there's rapid growth of tissue to screen for cancer. And then you can determine the location of that cancer and any metastatic progressions that occur. So if a tumor or another anomaly is found, its location can be determined by imaging techniques, and that is needed to do a biopsy or a treatment plan. So this talk will address the physics behind diagnostic imaging tools and radiological treatment devices that are used in modern medicine. The value of these tools is realized when trained, skilled medical staff use these tools to aid in their diagnosis and treatment. So what's the relationship to Mound? Well, actually, many medically related isotopes were enriched at Mound and our Stable Isotopes group, and other DOE laboratories have made significant contributions to developing imaging and treatment devices. The outline of this talk is shown here. Basically, we have modern imaging tools for diagnostics, which are ultrasound, X-rays, and CT scans. We'll talk about magnetic resonance imaging. We'll talk about radioactive source imaging, where we use radioactive sources like TC99 as a source within the organ and the body by injection. And then we measure the appearance of those gamma radiation using a camera. We'll also talk about low energy gamma emission, positron emission tomography scans. Then in the radiation treatments area, we'll talk about external beam gamma radiation, brachytherapy, and proton therapy. And along the way, we'll talk about the inventors and developers and users of these technologies and some examples of their products. Let's begin with ultrasound. So how does this work? Well, there's a block diagram of the essential features, and certainly the ones to focus on are the monitor, where you see the images that are created by the echoes that are received back. And then there is the transducer probe. The transducer probe is the generator of ultrasound and the receiver of the reflected signals coming back. Both of those are driven by a piezoelectric crystal with a high frequency RF drive to it, or it can read the displacement of the same crystal and the electricity that's generated with this piezoelectric crystal. The frequency that's used in this is like 2 to 15 megahertz, and our hearing normally is like 2 to 15 kilohertz or something like that. So this is about 1,000 times the frequency, and as a result, it has a shorter wavelength that can also resolve much smaller details in the echo process. So we look at a time delay of the echo. We send out a pulse, and it bounces off from various surfaces as it goes through the body. And then the total time of transit is whatever depth it's reached and then come back, divided by the speed of sound in the body, which is like 1,540 meters per second. Now, ordinary sound in air is about 300 meters per second. So this is like 5 times faster than the speed of sound in air. So the signal that is reflected back is related to density of the object reflecting it. So for bone, there's a very strong reflection because it's very stiff. And so that is normally ascribed as a white reflection source in the coloration of this signal. And then tissue itself is more gray-like, and liquids reflect very little, and so those are designated as a background for this. So as you look on the right, there are a few ultrasound images that have been created, and some of them have a dark spot in the middle, like here, and that implies that these are liquid-filled regions that are coming back, and so it could be a cyst that is filled with liquid as opposed to a tumor, which is full density. And then here at the bottom is the common reason why people take sonograms or ultrasounds, is to see the newly arrived fetus for a couple. The next subject is X-rays. X-rays were discovered by Wilhelm Roentgen in 1895 in Würtzburg, Bavaria. Roentgen kind of stumbled across this by accident. If you look over here, there's a device called a Crookes tube, which consists of a filament that emits electrons, and this is all under vacuum. And they were looking at the rays and how to bend them, which are the rays being electrons. But in the process, they also had a screen nearby, which was illuminated. And so, as it shows in the picture on the left, Roentgen had his hand over the screen holding it up, and he started to see bones in his hand. And the net result is that this same Crookes tube is generating not only electrons, but the electrons make X-rays, and the X-rays were shining through to the fluoroscope and giving the first X-ray photograph. The actual first medical X-ray was taken of his wife's left hand. Note she has a ring on it, and probably some evidences of arthritis in her hand also. So now, how are X-rays produced for our general use? Well, there's the simplest X-ray camera is a totally encapsulated tube inside it with a vacuum inside. And there is a filament that can generate electrons. The electrons are accelerated towards an anode. The anode is usually made out of tungsten, and the electrons crashing into the anode bury in deep and have interactions with the tungsten atoms. And what results from that is radiation. Is radiation, which is called Bremstrahlung. We'll see some examples of that. That is really breaking radiation. And then there's another characteristic radiation that comes out, which are like line sources here on top of the general Bremstrahlung background. So this is like, Bremstrahlung is like generating white light to illuminate something. So when you illuminate a person, you find the various lengths of wavelengths are available to see details. Okay, for higher intensity X-ray beams, these can be generated by using a rotating anode X-ray source, which conducts heat away from the device because of all of the energy that's deposited as heat. You need to carry it away with a high flux X-ray beam. And these beams are used in like chest X-ray or CT scans, which we'll see in a minute. But the protocols and experience of the radiologist define what the settings should be for a particular X-ray generator in order to produce high contrast, useful images. So what's Bremstrahlung and what is characteristic X-rays? Well, whenever an electron is slowed down, electromagnetic radiation is emitted due to the electron's deceleration. High energy electrons entering the tungsten anode, they have enough energy to penetrate into the tungsten lattice itself, where the electron sees the positive nucleus, and it can have some interactions that show a bending of the exit and of the electron, and a X-ray that comes out tangential to its motion. And then and that's the breaking radiation or Bremstrahlung. The characteristic X-rays come when an electron comes in, knocks out a bound K-shell electron from the atom, the tungsten atom, and then an electron from the L shell fills the vacancy that is left, and the energy difference between those two levels is released as an X-ray with that energy. Note down here the actual wavelengths of the X-rays get very short, down to something of the order of like 1/10 of a nanometer, which is 1 angstrom. And that's typically the size of a hydrogen atom, or 10 angstroms, like the size of any typical self-respecting molecule. The X-ray wavelengths generated, they have plenty of, or short enough dimensions to be able to, quote, see these small details. And so that's what makes X-rays useful. So how are X-rays detected? We saw an example of a fluoroscope screen, which is just zinc sulfide doped, and it glows green, or if it's hit with an X-ray. There's also X-ray film that's been used for many years as a permanent record of your chest X-ray in this case. But there's other digital means of doing it that are very important now, because they allow you to record them and pass them around to other medical staff. An example for a simple X-ray camera might be a dental detector, which is X-rays coming in and striking a scintillator, converting the X-ray energy into light energy, which is like ordinary visible light. And then with optical lens, you can image this onto a CCD camera and record the image, much like you would take a picture with your cell phone. If you have a larger chest X-ray that you want to take, there are devices that have a storage phosphor that can be placed here. You do the X-ray, and then you remove that X-ray plate, put it through a reader so that you can digitize the excitation that's occurred on the phosphor screen, and then record that, use it as the record of the X-ray, take intense light and re-establish a baseline for the phosphor for it to be used again. So this makes a reusable type device that yields the X-ray information that you need and want. So the next step of X-rays is computer assisted tomography, or CAT scans or CT scans. A lot of different names depending on where you are at. The CT scan was invented in 1972 by a British engineer, Sir Godfrey Hounsfield of EMI Laboratories in England. Now, if any of you are Beatles fans, you might remember EMI Laboratories. That's where the Beatles did their recordings, and that's the place that made all of the tapes and CDs and records and things. And so the success of the sales of that is thought to have been partially plowed into the CAT scan development later on. Godfrey Hounsfield was an engineer there at the laboratory, and he partnered with Alan Cormack, who he developed the math of tomography. This came from this South African-born physicist, Alan Cormack. He was a researcher at Cambridge at the time and Tufts here in the US later. So Cormack had X-ray experience from working at Precursor Hospital in South Africa back in the 50s. So he developed, once he had math skills, he developed a paper representing a function by its line integrals with some radiological applications. And this article was published in Journal of Applied Physics, a very prestigious journal. And in the paper, he demonstrates that a 3D object can be calculated from the line integral data of many points of view of an X-ray passing through the object and being recorded. You can take that data and a very good computer and recalculate an image of what it is that the X-rays went through. For this accomplishment, and we'll see some details of it, Hounsfield and Cormack were awarded the 1979 Nobel Prize in Medicine for their contributions in bringing the CT scan to medicine. Okay. So let's jump to the current use of a CT scanner, and this is like a third generation CT scanner for doing computed axial tomography. The X-ray source and the detector array are together on a circular device. Let's first of all start with the table on here. Starting on the left, you actually have a table where the patient lays, and the hole in the donut is where the patient moves through as the X-rays are being measured, and this kind of thing. So you can see the patient strapped down, not because they don't want him to get away, but they really don't want him to move. And so that way you'd get a blurry X-ray. In the center, if you take the hood off from the donut, you see that there's a bunch of electronics and some red lines. On the right side, there is this X-ray source. And on the other side, there are an array of detectors. And in the center is where the patient will go. And so you can see up here to the center, you can see that this is here, and this whole system, the detectors, the X-ray, and that rotates around the stationary sample, namely the patient. So this rotates a few revolutions per minute around the patient, and is taking X-rays as it goes. And meanwhile, as it's going in rotation, the table that has the patient on it is slowly moving into this X-ray generator and getting new slices of tissue that it's looking at and recording the images of. Now you can imagine that if you're going to do a full body scan, you can end up with an awful lot of data that is stored in a very large computer, and then to take the data and generate an algorithm using Cormack's math, that can be quite a computer process. So there's a combination of the hardware and the computer capabilities that can generate X-rays that are very, very valuable, like the ones that are shown here. Here's examples of some images from CT scans. The ones we're looking at top are a coronary CT angiogram taken of a patient where they put a dye in the blood that is flowing. And in this case, the patient had chest pain, and they are looking for regions of constrictions above blood vessel, and the arrows seem to indicate possible areas. And a solution for this might be to put a stent in or some other elective solution to the problem. The bottom one shows CT scans of lungs with potential for early cancer nodules shown in the red highlighted areas. This one on the left side and this one on the right side. So to the untrained eye, that might not look like that much, but the experience of the people that use these tools can get a great deal of information out of these high-resolution CT scans. Another 3D imaging technology is magnetic resonance imaging. And here we're going to talk a little bit about what is magnetic resonance imaging all about. Well, it starts by looking at the tool that we have. The tool is, again, a patient on a trolley that goes into the bore of a magnet. And the magnet is a superconducting magnet that generates a very large field, and we'll talk about that in a minute. But in the process, this magnetic field from a line pointing toes towards the head, this aligns any proton that is inside the body. Well, there's protons all over in a body that is basically hydrocarbons. So every carbon atom has 2 to 3 protons around it. And each of those protons acts like a little bar magnet. So it has a magnetic moment, we've labeled mu here. And that, in the presence of this magnetic field, it can precess around the axis at a particular frequency. And it's called the Larmor precession frequency, directly proportional to the applied field that we have here. Well, if you come and try to follow that by using a RF pulse that comes in with RF energy at the resonant frequency that this is precessing, you can grab a hold of that magnetic moment and have it point in a higher energy state by absorbing energy and pointing opposite the field. That's a higher energy state. So when you release the pulse and it stops, immediately this wants to relax back to the original low energy state. And in the process, it gives up some energy to the environment that it's around it. And that environment can be other molecules and other tissues, but it's unique to the particular proton that we were looking at. So each proton can give back a little signal, and those signals can be used to generate an image. Now, some of the practical features of magnetic resonance imaging being selected for your measurements. There's no ionizing radiation like there is with X-rays. So this is intrinsically safe. There are strong magnetic fields, however, and so no ferrous materials in your pockets. And worse yet is if you had a little metal shard of steel in your tissue from machining something, that could easily be a problem in the magnetic field of being torn loose. So there's a lot of screening of people before they get in, as do they have any kind of metal in them. They may have a metal knee or something like that, which is typically a stainless steel alloy that is non-magnetic. So that's okay. The other thing is it generates some noise. So as you're there laying and having your protons analyzed, it is very noisy because the RF signals that go through the coils cause them to flex, and they just kind of rattle against each other and generate some noise. The other thing is, if you look at it, the bore of this might make some people claustrophobic, and that's an issue. And so for them, it's probably best to have a CAT scan. So let's continue talking about magnetic resonance imaging. Where does it come from? What is magnetic resonance? Well, there's a long history of high-resolution nuclear magnetic resonance used for chemical structure investigations and material studies. The first NMR measurement was done in 1938 by Isidore Rabi. He got a Nobel Prize for that, for doing that unique thing. But the classical NMR that we use to study chemistry and some material studies and that, the physics of that goes back to 1944 with Felix Bloch and Edward Purcell. And they too received a Nobel Prize for their work. Basically, what it describes is a magnetic north and south pole and the magnetic field going through a sample, and the sample experiences RF frequencies at some defined frequency for protons. And so you excite those protons to align them opposite the field, and then you have a reading coil around the sample that when you stop the pulse, it measures the relaxation and gives you a signal out. And that result is you end up with a spectrum of protons that are in different magnetic environments due to the shielding of the electrons that they share with the carbon atom, in this case, for a favorite alcohol molecule, ethanol. So anyway, the hydrogen atoms, the blue ones on the left are associated with this shift. The one on the oxygen atom is here, and the ones on the two hydrogen atoms on the central carbon atom is there. So those are small deviations, like 2 to 4 parts per million. And so, but it can be used in order to determine chemical structures. However, this was enough of a standard function for nuclear magnetic resonance. You could only have a uniform field and things like that, that this made it very difficult for the inventor of magnetic resonance imaging, our friend Paul Lauterbur. He developed the concept coming out of being an expert in ordinary nuclear magnetic resonance. So what is the deviation and how did he come by that? Well, first of all, Paul Lauterbur was born and raised in Sydney, Ohio, 40 miles north of Dayton. He was trained at Case Institute, now Case Western. Got his Ph.D. in chemistry from the University of Pittsburgh, and he practiced there and at and later on at the State University of New York. But any proton must adhere to the relationship where there's a relationship between the applied magnetic field and the bore and the frequency that you are using for the Larmor tilting. That's 42.58 megahertz per Tesla. A Tesla, what is this? Well, it's 10,000 Gauss. So what's a Gauss? Well, a Gauss is like the magnetic field that we have for the Earth is about 0.6 of 1 Gauss. So it's not very strong, and that's at the maximum value of it. And so 10,000 Gauss is like 15,000 times the amount of the magnetic field of the Earth. So a very strong magnetic field. It would definitely suck a metal steel piece across the room. So getting back to what is MRI all about, in 1972, Paul Lauterbur had the insight that in a magnetic field gradient, not a uniform field, but if you made a field gradient, you could scan through the frequencies and you could find proton resonances that occurred that related to the resonance magnetic field at a particular location, X, Y, and Z. So now by finding these resonances, the one that you find tells you that the location X, Y, and Z of where did that signal come from to create this resonance. So that's the idea, is that you can do a spatial recognition of where do the signals come from. That allows you to keep track of what is giving what signal. Now, believe it or not, independently, Sir Peter Mansfield of the University of Nottingham in the UK, he was studying spin echoes and MRI signals, but he also did MRI signals in a magnetic field gradient. So in '59, he was working on sort of an NMR related thing, spin echo signals. In '72, he actually learned about Lauterbur's paper and claims about that you could find resonances in an extended object. Well, he had actually funding to pursue some related experiments. So in 1977, his group imaged a finger using a small bore magnet to test out the MRI principle that Lauterbur had found, and found that it worked. And this was intriguing enough to them that they found some more funding, and in 1978, they made a larger magnet so that they could put and do some whole body imaging with that. Then the first MRI scanner for clinical use was built in 1980, and that was done at the University of Aberdeen in England. And later on, it was on the market as a commercial device in 1984. I think the first MRI that I know of in the United States was probably in '88 or '89. And again, at a large hospital. But the net result of this is that in 2003, Paul Lauterbur, with the original idea, and Peter Mansfield as the first example of building it, shared the Nobel Prize in Medicine for their independent efforts towards development of MRI for medical use. Mansfield was named a Fellow of the Royal Society, big deal in England, and he was knighted in 1993. So he is Sir Peter Mansfield. Nothing so for Paul Lauterbur. He continued to work on MRI at SUNY Stony Brook on Long Island. And then he went to the University of Illinois in Urbana to finish his career in MRI. And as it indicates, Lauterbur died in 2007 and Mansfield in 2017. So one final thing, how is this actually used in the operation area? The picture is what we show, and the main magnetic field is defined. That makes what the Larmor frequency is for resonance. Then various pulsing of coils in the X and Y direction, these various colored coils, can generate a pulse that turns the spin of the proton to face against the magnetic field. And then you can measure the relaxation times T1 and T2. And those are the characteristic information that tells you what kind of environment does this particular proton sit in. And from gathering all that information that you gather and massaging the data in a computer, what comes out are images like this. The MRI provides high-resolution images of the brain and other kinds of tissue throughout the body. But let's just look at the details of the normal brain scan on the left. Can show in very, very high detail things that even I can recognize, like olfactory nerves here that go down to the nose, and probably optic nerves that are entering the brain from the eye, and many other features. So it's very easy with the MRI to see anomalies in the brain. For example, a tumor present here is easily identified as different tissue than what the normal brain tissue is in the area. And so it shows up assigned a different color and can be easily identified. There's a new application of MRI, which is functional MRI. Functional MRI measures small changes in oxygen level and blood flow in the brain. These are measured from changes in MRI images taken successively in time. And this can identify our brain function here as this person is looking at someone doing exercises on a screen. You can see that different areas in the brain light up as the information is processed. And then the pattern triggers something totally different. And this is something interesting that they are, quote, understanding. So functional MRI looks at the brain's functionality and is available for studies of how cognition occurs. The main one for hospital use is the MRI that measures physical tissue presence. And so it would look for like brain tumors and things like that. Let's go on to a new area, which is two-dimensional nuclear imaging of organs, tissue, and flow versus time. And this is done with radionuclides and a scintillation camera. The list of nuclides is given here on the left. There are a number of them that have 100 to 300 kiloelectron volts of gamma energy, which is not too severe. It's not damaging. So you can define a crystal detector that can accept that kind of gamma energy and give a conversion of that photon energy of the gamma ray into a visible photon that the phototubes can actually measure. One we're going to concentrate on is technetium-99m, and it has 140 keV. It's chosen for about 80% of all of these kinds of imaging tests because it has a 6-hour half-life. And so you give an injection, you've got a number of hours to look at how this progresses through your body and what kind of signals it gives. But as a matter of time goes by, within a day or so, it's pretty well gone. Others can be used for specialty imaging of certain organs. But here, and let's look at the gamma camera. This consists of a chunk of lead, a slab of lead that is like 2 to 3 centimeters thick, with small holes drilled in an array pattern so that the gamma rays can go down through this channel and be recorded. And the aspect ratio of the diameter of the hole to the length of it is such that it's a very narrow field of view that is looking. So it's the gamma rays that come directly up from a particular place. And by looking at where those gammas come from, you can get a direct image of this organ that is before this. This gamma camera was developed at Lawrence Berkeley National Laboratory in California, in Berkeley, California. Hal Anger developed this camera in 1957. So nuclear imaging of many organs or body functions is achieved by using eluted sodium pertechnicate. Let's go through the chemistry, which originated actually at Brookhaven National Laboratory. Technetium-99 comes from the radioactive decay, the beta decay of molybdenum-99, 67-hour half-life. And the technetium-99 is another metal that accumulates along with the molybdenum. So there's betas that are given off during that decay. And as the technetium accumulates on the surface, Brookhaven developed an elution technique that you could take the technetium that is developed on the surface of the moly inside of a substrate that has all of the materials on a column. You can elute the technetium by passing a salt solution over this, sodium chloride and water, over the column, and this technetium is eluted or washed off as sodium pertechnetate. And that is a chemical that can be absorbed by most organs. And so in its high purity form that they have, you can actually do an injection directly into the arm of a person, and then it migrates through the body fluids and arrives at various organs. So here we show a couple of examples of it at early in the exposure time, 30 for the injection time. You can see the things like thyroid, lungs, and heart tissue, and maybe liver. These show up at being imaged, that you can actually discern them with your gamma camera. As time goes on, this develops into also the digestive system so that you can image that. So in some cases, it's a matter of a waiting game to have the material appear in the organ of interest for you. But this can all be recorded and played back and analyzed at a later time. Now, the current sources of molybdenum-99 to give this technetium that everybody wants, they come from all over the world. Excuse me, let me just move this over here. So they come from all over the world. But the fact is, there was nobody making it in the United States. So this is a security issue to the U.S. In that you don't want to have your hospitals shut down for testing due to a lack of this radioisotope. So the closure of the reactor at the Chalk River in Canada precipitated Department of Energy and NNSA to support production of molybdenum-99 using some of the research reactors that are available at universities around the country. And these are DOE-funded facilities. So, for example, WSUR, the Washington State University Research Reactor at Pullman, Washington, and the University of Missouri reactor at Rolla, Missouri. Those are both candidates that have now, in 2018, received authorization to be able to make Moly-99 by using low enrichment uranium targets with their reactors, neutrons, and then do the chemistry separation to get the Moly-99 out. By low enrichment, what they mean is 20% U-235 to give enough material to make the chemistry worthwhile, but it is not a nuclear bomb material. So the net result is it's a safeguard to be able to use low enrichment. Some of the new projects that NNSA is working on is one at Shine Medical in Janesville, Wisconsin, and together with Phoenix Nuclear in Madison. And this is to generate Moly-99 from an alternative generation method. Again, it involves low enrichment uranium, but you take and use an accelerator-based neutron source incident on a low enrichment slurry, where the chemical extraction can be done with the slurry in a different area. And so you can make an actual constant flow process for this to be generating Moly-99. The neutrons for this device would come from deuterium ions that are accelerated into tritium gas for a fusion reaction, which is the normal DT fusion reaction. And the accelerator neutron source, which exists already, is used as a neutron source for doing neutron radiography. And so that can be put into use with low energy uranium, and this is due to come online in 2022, barring COVID delays. PC99 is the radioisotope of choice for many imagings. Again, 20 million diagnostic nuclear medical procedures are done using it each year. If you have a 6-hour half-life, it means that one day after the injection that you received, there's only 6% left. 2 days later, it's 0.4%, and that goes down from there. You're given an information card indicating that you've had this. So if someone measures radioactivity on you at an airport or something, you can make it through to your flight. The number of procedures that are identified here, and those related to the heart and bone scans, and that seem to be the dominant. The last one of these scan methods is positron emission tomography. Again, Brookhaven National Labs, they developed the PET scanning methodology and also the radiochemical that you use for identifying and producing positrons so that you can image the tissue. So positron emission tomography uses oxygen-18 as a target for protons to make the fluorine-18 that you need, with a proton accelerator right at the hospitals where they do the PET scans. For example, Kettering Medical Center has a 11 MeV cyclotron in their basement, and they can make these things. So if you take H2O18 and hit it with 11 MeV protons, you generate fluorine-18, and a neutron comes out. Basically, the incident proton knocks a neutron out and stays there as an extra proton and makes the oxygen into fluorine. Now, this fluorine is attached to a sugar carbohydrate molecule and given to the patient. The sugar is taken up by rapidly growing cells. Usually we call those cancer cells. And the fluorine-18 decays by positron emission. So the positron emission, it makes it go back to oxygen-18. So this positron, and if you look in the lower left side here, you see that there's a positron emitted from the fluorine 18, and it finds another electron somewhere very nearby. And in that process, those two positive and negative electrons come together and they annihilate each other. No kidding, this really happens. And that result is two gamma rays that are directly opposite, ejected directly opposite each other, 180 degrees apart. This is in order that the net momentum of the process is zero, which is basically what it was when the positron and electron wandered into each other. So this annihilation occurs generating two half MeV gamma rays that come out, and they are 180 degrees apart. And so using that information, one can generate a way of measuring where did this positron annihilation actually occur? Well, there are a number of other positron sources, but fluorine-18 is the practical choice that is used. The other thing of interest to us here in Dayton is that 90% of the medical supply for oxygen-18 for PET scans is enriched as a stable isotope at Cambridge Isotope Labs here in Xenia, Ohio, probably done by former Mound personnel. What we're showing over to the right is an image that's rotating, and there are various on the background CT scan image, there is the colorized regions where there are different levels of concentration of the PET scan signals coming, and that would directly relate to the amount of cancer that is there. I mean, this is the assumption. Okay, so how do you use this? Well, the practical way is to have a combined PET CT scan to use the complementary images that they both make and put them together. So again, we have our CT table where the X-ray and detector system rotates around the patient, and you get an image of the whole body. And then simultaneously with that, you measure with fixed position tapered scintillators the detection of the two 180-degree apart 511 keV PET gammas. These two gammas, you can tell that they're related and came from an annihilation event because they have to be detected within 1 nanosecond of each other. And that's basically the net distance difference that they can travel between them. So the first criteria is you measure a gamma signal in the gamma cameras, and you look for a signal at the camera that is 180 degrees across from you. Okay? And then you say, are they within a nanosecond of each other? If they are, then you can look more carefully at the time arrivals of those signals. And you can look from what's the position in distance within the body from the normal or the center line, the equidistant point that they would have had to travel. And from that, you can place the tissue that is generating that at places like shown here, and then they can be superimposed on the CT scan to give you that you found cancers located here, and you can see near what organ and how are you going to biopsy that. So that is the end of our diagnostic treatment methods. We want to finish up here with looking at radiological cancer treatment methods. And the ones we'll look at are external beam gamma radiation. We'll look at the gamma knife, which is a proprietary name. We can look at brachytherapy and proton therapy. These are the four that are the major radiation-related treatment methods for cancer. Now, the premise on all of these methods is that they use gamma rays or particle beams focused on the cancer site to basically damage the DNA of the cancer so that it can no longer replicate. That's, quote, how you kill it, is if it can no longer replicate, it eventually withers and dies itself, and that's the way the cancer goes away. So let's look first at the external beam radiation treatment method. Here there's a collimated gamma beams from cobalt-60. Cobalt-60 is on a cylinder that compressed air can move it into position so that you get a beam. The beam is defined by the collimator leaves that are in it that are lead absorbers. And so what comes out is a very, very well-defined beam that is along a particular axis. So knowing that beam is coming out, not something you will see, but you can take this gantry and you can have that beam enter the body from different points of view, and it's all focused to cross where the tumor is located within the body. So you may have to raise or lower the table and that in order to have the crossing point be where the tumor is actually located. So normally the treatment for this is multiple times per week, with multiple sessions every day, and with at least a day of recovery per week in them. So a very common protocol would be 5 gamma treatments per week for 3 to 5 weeks, and that would give you the weekend to recover from it. And it's literally the tissue that is not the target of the tumor, but the intervening tissue has had some damage, and there is repair that can go on. Much like you recover from sunburn, the tissue can be repaired by the body as a normal recovery thing. And the recovery rates are known well enough so that they define the protocol for how much of a treatment you get and how often. The gamma knife is a variation on the cobalt-60. There is no knife, but rather there are many gamma beams that come from cobalt-60 source, and they are all focused on a very, very small volume, where the intensity of the converging beams is intended to damage the tissue and again kill the cancer by damaging the DNA. So the patient is put on a support table, and this is moved in and out to control and up and down to control the treatment volume and to start and stop the actual treatment process. So this is the system that is called the gamma knife. Another one is brachytherapy, which involves physical insertion of radiation seeds into the tumor region itself directly. Now, when it comes to doing cancer treatment, there are multiple choices that a patient needs to address and choose one that they're comfortable with. One of them is surgery, which is a very good method itself. Another one is chemotherapy, which has been done and much tried and true and very highly recommended. There's another one called brachytherapy, and that's not used that much, but it is available. And this is where you have seeds, radioactive seeds that are emitting beta particles, something that has enough energy to kill the tumor, and you insert them in close proximity to where the tumor is, like right in the middle of the tumor. So some of the applications are for prostate cancer, for uterine cancer, maybe breast cancer, and radiation in post-surgical areas, like if you remove a brain tumor and you're not sure you got all of the edges, you might want to put in some seeds to kill the remaining area, and thus eventually the seeds become inert and they no longer do anything. Then, of course, external beam radiation therapy, but then there's also proton therapy that is too new to be listed amongst the 4 that are here. So in the case of brachytherapy, here the example is shown someone with lung cancer, and they know where the tumor is located from imaging work that they've done. You can, in fact, do a direct placement of this directly in the tumor area and let the radiation of the beta particles do this. Going down to the last one here, the first proton beam for cancer therapy was done at Loma Linda University in 1990 as a joint project with DOE's Fermi Lab. Fermi Lab is about 30 miles west of Chicago, and it is a high-energy lab, much like CERN and installations like that. But they know how to build synchrotrons, which are proton storage devices that are used for high energy experiment physics, or in this case, protons are used for cancer treatment. So here in the picture is shown a device that is the synchrotron storage ring, 20 feet in diameter, and inside is a vacuum under which the protons are confined in a ring by magnetic fields, and they are stored there until you need them. As needed, 1 to 5 beams of proton, this is at Loma Linda, can be diverted and steered by magnets to a treatment room. So there are 5 different treatment rooms. So within a treatment room, the proton beam is further steered and focused onto the tumor from different angles, and depending on the amount of tissue you go through, you may need to alter the energy of it. And you can do that at the endpoint of the proton beam control in the actual treatment room. So what's the deal about proton beams? Well, over here in the bottom right, it shows that protons' penetration depth is directly proportional to the energy in MeV that is given to the proton. And the energy loss, you can see as it goes deeper into this material, which is like high density plastic, you can see it has a fixed energy loss that grows, and the slower as it slows down, it loses more energy per centimeter, and it deposits more energy as it goes along the way. So the idea is to take these proton beams and have them end their energy at the boundary, far boundary of the tumor. And then you can work your way back in destroying portions of the tumors. You can steer them to get whatever the volume of the tumor is. You can do the destruction that way. But the idea is the most energy is deposited in the tumor near the end of its flight. So there's less radiation damage to the patient en route to the tumor site. So an example of this is if you look at gamma rays from like a cobalt-60 source, the gamma rays enter, hit the tumor, but they also exit the other side. And so here we're showing the photon gets absorbed uniformly as it goes along the way, all the way through the tissue, and it exits the body. The idea of a proton is that it deposits its energy here, and then it stops. Very little straggling beyond here, and then you can stop with the tumors here once you know that you've covered the whole volume of it. So here it shows that the proton beam stops at the designed distance. So this sounds like a good deal. Why aren't there so many of them? Well, basically cost. To build a proton beam therapy treatment center is a very large cost. So currently they are regional. The nearest one for us is actually down at Children's Medical Center, just north of Cincinnati. And it turns out that children that have cancers that need to be treated, the fact that you don't have a straggling exit beam is important for them to recover and not have it damage them for later in life. And so it's thought to be the method of choice for children. There's probably also another proton beam up at Medical Center in Cleveland Clinic. Winding up now, all of these things, or at least the radiation ones, have a dosing that is incident on each patient. We look at the recommended dose by the NRC, the Nuclear Regulatory Commission. They say that a yearly dose with no side effects is 50 millisieverts. Well, if we look at background radiation, basically you have something like 6 millisieverts a year that comes from cosmic rays and from radon and things like that that everybody is exposed to. And so we all endure and survive that. But the elective amounts of radiation that we receive are here, like a chest x-ray is not very much, nor is a mammogram, certainly not a dental x-ray. But if you look down at this list below, a PET scan or a heart stress test or other ones have like 10 millisieverts. And so you don't want to have many of those in a year, certainly, and probably not too many in your lifetime. So that's the downside of these radioisotope detection methods. So our summary. Multi-use radiological imaging tools provide diagnostic information, and the ones we looked at are X-ray, gamma imaging, and PET scans. There are multiple treatment methods for cancer which use collimated cobalt-60 gamma ray sources, implanted sources, the brachytherapy, or proton beams. So that was the two areas that we were looking at. But the other information that was interesting to me, at least, is that the Department of Energy has had an active role in developing many of these new diagnostic tools and treatment methods. So it clearly is a partnership. And just kind of as a laundry list here, Lawrence Berkeley National Laboratory, first of all, they gave us the cyclotron that generated an awful lot of chemicals in the periodic table. They are the source of iodine-131, which was used as a treatment for thyroid cancer for many years. And they also are the source of many other medical isotopes. They're the source of the Anger gamma camera, and they have been the source of heavy ion beam therapy methods beyond the proton beam therapy. Brookhaven National Laboratory, they gave us the technetium-99 generator, which is the Molly cow that you can milk to get the technetium as you need it. They also developed positron sources for PET scans. They are the source of Valium-2001, which is used for heart stress tests, which we didn't cover directly. The National Energy Technology Laboratory in Albany, Oregon, generated a medical opaque stent alloy, such that when you take an X-ray of this stent in place, you will see it on the X-ray, and you can check, is it deployed open, or has it been dislodged? Has it migrated? Some things like that. So apparently predecessors of this were not visible easily by X-rays. Fermi Lab with Loma Linda University gave us proton beam therapy, and there have been a number of follow-ons to that. And then some of the latest research at Washington State University and Missouri University to generate Moly-99 as a US source, and then to try this new Moly-99 production method at Shine and Phoenix Nuclear. Thank you for your attention to this. There's been an abundance of information that is on the internet on all of these instruments and procedures for your further study if you're so interested. All of the information in this talk came from the internet with some experiences and common sense involved also. But if you have questions, I think the easiest way to direct them is to contact me by email. And a good email for me is ellefson@moundtech.com. So thank you for your attention, and have a good evening.
Yes. Okay, well, thank you, Bob. We appreciate all the effort you went in to collect that and the role that physics and chemistry has played in modern medicine, I want to point out, as soon as I bring it up, oh, here we go, that this session has been recorded and will be posted on YouTube. And we've, in fact, almost all our presentations in 2020 are now available on the Mound Science and Energy Museum Association YouTube channel. We have our own channel, not a lot of subscribers yet, but here's the link. If you can search for that on YouTube, you'll see the presentations that we gave this year. And we're also bringing up a number of our archived ones that were presented earlier and going to have those available. So there's a chance to see those. A lot of them will relate to topics of the Mound Laboratory and DOE areas that we've worked on. So it is an opportunity as the long winter months proceed for you to get a chance to review those. Now, let's see if I go next slide. There won't be a seminar in December from the Mound, but we will have one in January, the fourth Wednesday, and that's going to be the 27th of January. Again, the start time will be 7. And our topic is going to be Dayton history, past, present, and future. Mandy Askin, who's the manager of the Mound Cold War Discovery Center, will give an updated highlight of what's been going on with Dayton history, both before the pandemic started, what's going on now, and what the future will be. The Mound Museum has been doing some renovations, so she'll probably talk about those plans too. And we are working on new presentations for 2021. We'll be announcing those as we set up our schedule. We will almost certainly be virtual through the first half of 2021 and then go from there. So again, I want to thank Bob Ellefson for all the effort to prepare our presentation tonight, and for Jack Melke for coordinating the presentation and presenting it to us tonight, and you all for coming by, listening to us, and thank you again, and may you all have a great holiday season and get well, and we look forward to hosting you all again in 2021. So good night, and best regards to everyone.